Have you ever stopped to think that absolutely everything in the universe is spinning? The moon spins around the Earth. The Earth spins on its own axis and at the same time orbits the Sun. The Sun, in turn, also spins. It travels on a path around the center of our galaxy, the Milky Way. The Milky Way also orbits the center of gravity of what's called the local group of galaxies, which includes more than 50 of them. And this entire group is still spinning within an even larger structure, the Virgo supercluster, and so on. One rotation inside another, like an endless cosmic ballet. Even for space travel, spin is essential. Before landing on the moon, for example, spacecraft must first enter orbit, both around Earth and the satellite itself, before making a controlled descent. And don't think this movement is exclusive to large scales. In the quantum universe, there is spin too. Electrons spin around the nuclei of atoms. And beyond that, every subatomic particle has what physicists call spin. Spin is a fundamental property, like the DNA of a particle's motion. It isn't exactly a physical rotation as we usually imagine, but rather a kind of intrinsic angular momentum, like mass or electric charge. In the case of the electron, this spin even creates a small magnetic field around it. Protons, neutrons, antiparticles, all have spin, and this characteristic is inseparable from them. From the moment a particle is created, it is born with this intrinsic motion, which depends on its density and energy. Now, as these particles began clustering together and growing larger over time, gathering matter thanks to gravity, they also started acquiring angular momentum. This angular momentum is what determines whether an object spins on its own axis or orbits around another body, like Earth does with the Sun. In fact, this tendency to spin has a curious effect. It gives objects in space a spherical shape. That's because gravity pulls the mass of any body toward its center. And the greater the mass, the stronger its pull. So you might wonder, why don't planets simply collide with each other? The answer is, if everything were motionless, indeed all matter would tend to collapse into a single point and collide. The universe would lose its balance, but the truth is, nothing is motionless. Everything moves. The velocities of celestial bodies differ, and that creates a dance of movements, a choreography that follows a powerful rule: inertia. Inertia is the tendency of a body to keep moving or remain at rest unless acted upon by an external force. And in space, where there's practically no friction, motion can be preserved for immense stretches of time. This is what we call conservation of angular momentum. Because of this conservation, bodies in the universe keep spinning and orbiting, whether in circular paths or elliptical orbits. Sometimes it's true this dance can be interrupted by a collision, but even then, angular momentum is preserved. It's just redistributed. In space, since the vacuum isn't completely empty, velocities also add up or cancel out depending on the direction of the objects. And this leads us to a fundamental conclusion. There is no absolute rest. Want an example? If Earth were destroyed by some catastrophic event, its fragments would keep orbiting the Sun. They would retain the angular momentum inherited from the original planet. Fortunately, that's not in our near future. And even though Earth's rotation is gradually slowing due to the moon's gravitational influence and the faint resistance of space, it will take billions of years. Long before that, the Sun will have burned through its fuel and ceased to exist, and humanity will likely be long gone. With this knowledge, we understand that any interstellar object entering our solar system must have been launched at an extremely high speed, so high that it could overcome the gravitational pull of its own system. Take the object Oumuamua, for instance. We still don't know where it came from, but we're sure the velocity it reached to escape its home system was extremely high. That usually only happens after explosive events like collisions or the violent death of a star. That's what's called escape velocity. Have you heard of it? Basically, it's the minimum speed a body needs to break free from another celestial body's gravity. For example, to escape Earth's gravity, you'd need to reach 11.2 kilometers per second, more than 40,000 kilometers per hour. But even at that speed, we'd still be trapped by the sun, orbiting along with Earth. To escape the entire solar system, the challenge gets tougher. We'd need to reach 43.5 kilometers per second. But that insane speed doesn't remain constant. As the object moves away, the sun's gravity pulls and slows it down, gradually reducing its speed. That's why sending a probe outside the solar system isn't so simple. That's exactly why, in the case of the Voyager probe, scientists relied on a clever strategy: gravitational assist. Instead of just using fuel, they took advantage of the gravity of giant planets like Jupiter and Saturn to slingshot the probe. Sequential gravitational boosts that increase speed without spending more energy. This technique works because in physics, energy is conserved. So, if we want to launch an object fast enough to become interstellar, meaning leave the solar system and drift through space, we basically have two options. Either we use brilliant maneuvers like this, or we rely on colossal explosions like supernovas that hurl matter at unbelievable speeds. But what if we wanted to go even farther? Our galaxy itself has an escape velocity, 537 kilometers per second, about 1,280,000 kilometers per hour. That's right, we'd need to reach nearly 2 million kilometers per hour to escape the Milky Way's gravity and head toward other galaxies. So far, we've understood a bit about why objects spin, how gravity works, and the role of angular momentum conservation. But one burning question remains: why has everything in the universe been spinning since the beginning? Where did this original push come from? Could the universe itself have started spinning? This is a mystery that still puzzles scientists. Some studies suggest a slight asymmetry. A small majority of galaxies seem to spin in the same direction, around 1% to 2% more. That could just be an observational bias, but if confirmed, it could indicate a preferred direction in the universe. It may sound small, but it's significant, especially because if the universe had started in perfect balance, logically, we should see half the galaxies spinning one way and half the other. This slight bias toward one direction could indicate that, yes, the universe may have started with an initial rotation, and that would change a lot. In fact, some theorists suggest that this original rotation could be linked to dark energy, that mysterious force accelerating the expansion of the universe. Perhaps what we call dark energy is actually the effect of a colossal centrifugal force generated by the rotation of the universe itself. This idea, however, has no observational support, no direct proof. Research with the cosmic microwave background, that primordial light from the Big Bang, hasn't detected clear signs of universal rotation. But that doesn't rule out the possibility. Maybe it's spinning so slowly that we simply can't perceive it. Just like our ancestors once had no idea Earth spun on its axis. In fact, some studies suggest the universe could take 6.3 billion years to complete a single rotation on its own axis. That number is so colossal that, to us, it feels as if everything is standing still. And if we go further into speculation, could our universe itself be spinning inside a larger system, like a planet inside a solar system? And if the multiverse is a structure where different universes spin and even collide with each other, like planets creating cataclysmic events like the Big Bang? Fascinating, isn't it? The truth is, we could keep speculating forever and still not reach a concrete answer. But one thing is certain: the further science advances, the more the universe reveals itself to be strange, complex and astonishing. It looks like a giant gear, perfectly tuned, and we humans are just a small piece of this immense cosmic machinery.